The openings and saw the big ones.
If I am trying to deal with more than two groups, I have a problem. When we were doing our t-tests, trying to compare, hey, the average from group 1 different than the average from group 2. If I only had two groups, then I set my alpha to 0.05. There's a 5% chance that I'm wrong, thus a 95% chance that my null hypothesis is right. But what if I had three groups? I'd have to do three different tests. I'd have to test group 1 against group 2, group 1 against group 3, and group 2 against group 3. But every time I do the test, it's only 0.95 that my null hypothesis is accepted as opposed to rejected. 5% chance something weird will happen. Assuming there's no sort of interrelational effect that would cause these tests to depend on each other's results, then they're independent of each other, which means the 95% chance in the first one and the second one and the third one, if I'm doing and, I need to multiply those together. Grab your calculators. What's 0.95 times 3? Times itself 3 times. Say again? So instead of having a 95% I'm right, to get all three of them right, I have now an 86 chance. It's gone down quite a bit, right? If I had 4 groups, I'd have 6 different tests. 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. What's 0.95 to the 6th? .95 times itself 6 times.
0.74.
0.74. I've gone down to 75% chance of getting all of them to agree. This is horrible. What I thought was going to be a 5% is now 26%, right? It's at 0.74 or 14%. So if I have more groups, I don't want to do t-tests. So a bunch of statisticians talking about this idea, a guy by the name of Ronald Fisher says, what I really want to think about is the way in which the variation occurs within each group, right? Because if I did a sample from group 1 and a sample from group 2, that's what I'm comparing, but now I have a sample from group 3 and group 4. Each one will have a little bit of internal variance. But if something's different between the groups, the variation between the groups should be a lot bigger than the variation within the group. Just like with our discussion about our sales higher at store 2 than at store 1? Are they different? Whichever way we want to phrase it. I need to look at the variance between 2 and 1, and that was what our t-test did. With more groups, this is hard. So along comes Fisher. And Fisher creates a new distribution. Just like Gossett created the t-distribution for the t-test, we have this new F distribution. Well, they named it after Fisher. And he's going to do the same thing. He's going to say, hey, if we're really out there on either end, whether we're to the low end or the high end, there's a chance that there is more variation between the groups than there is within the groups. And what Fisher did is he created this F score. And I'm just going to write it as between over within. It's a lot more of taking the deviations and squaring and then averaging and divide. There's a lot more that goes into constructing this value. And he's going to decide if this is big or small. And if it's big, we're going to get a small p-value. Again, there's a picture. Now, the F-test looks a lot different. The F distribution is actually asymmetric. It's no longer that same kind of normal shape, that same kind of T shape where we have it on either side. It's always positive because those withins and betweens are always squared. They're positive numbers. But he's going to say, hey, if you're out here or down here, that's weird enough. You should reject the null hypothesis. Large F values give us small p-values. So I'm going to play the same exact game. I'm going to set up a hypothesis. I'm going to use this Fisher test to figure out whether or not I have a small p-value. By default, what am I comparing that p-value with? Fill in the blank. 0.05, exactly. Now I can change that. That's our alpha value. That's our sensitivity. The default one is 0.05. I reject my null hypothesis. But here's the best part. In every analysis of variance idea where we do an F test, we're always testing the same null hypothesis. When we were doing our t-test, we were checking to see if mean 1 was the same as mean 2, or if it was different, or it was higher or lower. In an analysis of variance, I'm always testing. They're all equal. What's the alternate hypothesis? The two hypotheses have to be mutually exclusive and completely exhausting. At least one is different. They don't all have to be different, but at least one has to be different than the others. Because this is an analysis of the variance, that's actually the name of this test, the analysis of variance. Now, because I am only concerned with one idea, let me give you an example. I have here a sample of GPAs from 4 different business majors. Do students in one particular major or do better or worse than another? Or are these majors all roughly equal in GPA? So here, I only want to know if changing major within business results in a different GPA. One thing I am concerned about, which major you are in and whether or not that has an effect on GPA. This is called a one-factor ANOVA. We can have more than one factor. I'll save that for next semester. Grab this data file, the L16 file under Module 3, and throw it into Excel. That's not the right one. That's the right one. Here's our data. I have never in my entire career in mathematics and statistics ever done an ANOVA calculation by hand. It's long, arduous, and ugly, and it ain't worth it. Again, there are lots of different pieces of software that will do an ANOVA for you. There's an ANOVA built into the graphing calculator. But I'm going to use what I consider to be the most common version of this, and that's an Excel. Again, to find the tests I'm doing, where do I go? Wrong. My data analysis tab. That's exactly right. So I go to data in the ribbon, and all the way on the right is data analysis. When I click on that, there's my options. I scroll up and I find 3 different versions of ANOVA. I'm only dealing with one factor. Single factor ANOVA is the top. As I said, we can do different kinds with more factors. There are 2 different 2-factor versions. There are things called multiple ANOVAs, or it's abbreviated MANOVA rather than ANOVA. Put the M in front. I'm going to do that single factor ANOVA. Click. And now it asks, where's the data? Well, I'm going to go highlight the data. Here's the data. Then it asks me how I arranged it. I have this in columns. You could equally have this data in rows, but I need to select which one it is. I put the labels are highlighted. You see how they're inside the dotted box? So I need to check labels are in the first row. My alpha is set to 0.05. I am checking to see if average GPA is the same across these four majors. I'm going to ask it to do all this stuff. I'm going to put it in a new worksheet. So I'm just going to click New Ply down here and hit OK. And it did a whole bunch of junk for me. I'm going to spread this first column. There. Now, this just spit out all these results. There is a difference, yes or no. My null hypothesis was that they were all the same. The alternate is at least one is different. How do I know? Joe? Which one? That p-value right there. There's my p-value. Now it actually did give me two different f values, you'll notice, to either side of that p-value. On the left side, I have an f, and on the right side, I have something labeled f critical. The f that doesn't have a label on, the one on the left, is the one that we calculated doing all the calculations I told you happened behind the scene with the between versus the within. As a matter of fact, if we look further over there, you'll see numbers that say between groups and within groups all the way on the left. And those SS's, those are the sums of the squares. DF is degrees of freedom. And then they did a whole bunch of calculating here. But he gave me the F value, and then it went and said, oh, you said 5%, right? Let's go to where the 5% line is, draw a line. That's our critical value. We're bigger than that. The p-value, the likelihood that we would be up there is 0.030389, all that garbage. That tells me what I should do. So now the answer is, what should I do? Felix. We said alpha was 0.05. If I'm less than that, I reject the null hypothesis. I'm out there in that rejection region. 0.03 is smaller than 0.05. I reject. That means that at least one of these majors has a statistically higher GPA than others, or a statistically lower GPA than the other. It's just different. I didn't say which way, but that's where I can look at the top block, because the top block actually gives me the summary of all of the groups. It shows me within each group, this is the within part, what the average is and what the variance is. Please notice the averages. Look at the four averages we have here. What do they tell me? Felix? But now I can actually look and see which ones are which, right? It looks like they're actually written in increasing order, and that the accounting majors have the hardest time in their program, and the marketing majors seem to have the easiest time in theirs. And if I look at the variance for the accounting group is the largest. So even though they have the worst average GPA, they have the most spread in that group. It means there are some really good accounting majors and some that aren't so good. Around an average of 2.83, it's a B. I'm okay with that. But compare the difference from 2.8 to 3.37. There's a substantial change. And it looks like those lower three majors are closer together because they have much smaller variances. 0.03, 0.09, 0.066. Those are much smaller in variation. So having this piece of information given to me, I can now say I only had to do one test, not six. 6 individual t-tests here would have lowered my chance of getting it right 95% to 74%. Instead, I did one test. I'm much happier with it. Questions? ANOVA, it's correlated multiple ANOVA, become far more useful when I'm looking at lots of different factors influencing behavior. Things like what causes a person to buy or not buy a particular product. What causes a person to choose to go to a store as opposed to stay home and shop online. All of those pieces matter. But here, all of my data was numerical. All of my data was easy to find. But we did a lot of other type of summaries. We did pivot tables, right? Talked about those and the way they work from our data collection. Let's close that. What if I'm dealing instead with categorical data? So what the hell, what categorical data versus numerical data? What was the difference there? I did talk to you guys about what kind of data we have, right? Whether we have numerical or categorical. What is a categorical data ID? Am I hallucinating doing this? First time through this class. And I am teaching the stats class at the same time. And I know I did it there. I thought I did it here too.
Or maybe we can put it in head rows, the data,
Yeah.
and the numerical data is like memorable differences.
So it's actually looking at numbers when I'm doing numerical, but categorical is just categories, right? So what color is your car? I'm not going to put numbers on that, right? Gray, black, silver, green, blue, red. I'm not going to put numbers on those. I could, if you really want me to, I could put numbers on those. But would the numbers matter? Not in the slightest. If you're going to go shopping, do you prefer to go to a store or do you prefer to stay home and shop online? I'm looking for LED light bulbs with a small candelabra base to fit into an overhead light fixture at my house. I can go down to Lowe's, I can go to Walmart, I can go to Home Depot. I know they have them. I could get on Amazon, order them, and have them delivered to my house. Right? Does age of the person shopping make a difference? I want to know if those are related. Whether or not I have a choice of, oh, we did energy drinks the other week, right? So energy drinks. Versus where you live. Maybe what type of car you prefer to buy. Or what type of computer you prefer to purchase. All right, all you athletes. Performance versus training regimen. Going to do aerobic workouts, you're going to do treadmill workouts, you're going to do strength training. The answer is probably you're going to do all of them, but some of the pieces you'll emphasize more than others. Does it make a difference as to how you do when you actually go out there? If I want to see if these two things are related, I could label all of my training methods, determine whether people perform above a certain level or below a certain level, and then I'm going to test to see whether or not these two things are related. If there's no relation between these two things, we're going to call them independent. Independent variables, nothing to do with each other. And we're going to create a contingency table. This is very much our pivot table idea. I've got rows and free columns for the two different variables. R for rows. C for columns. Now, I don't know how many training options and how many performance options I have, but I've got so many rows and so many columns for each of these two variables. And then in each block in here, I'm going to have a number. So here, that number F tells me how many times people using a one training had B1 performance. Since it's got a 1 and a 1, I'm going to put those two numbers there to keep track of what I'm doing. And that means in this one, I'm going to use the first row and the second column. And down here, I'll have F1C, right? And then here I'll have F21 and F22 all the way up to F2C. And when I get to the bottom here, it'll be FR1 and FR2 all the way out to FRC. Now I need some numbers. I need to add up in each row, and I need to add up in each column. So I'll get a row total for each row. I'll get a column total for each column. And then I'll have a grand total. How many people did the study? This looks like an absolutely insane setup. Here's what the idea looks like in a practical example. Do people prefer shopping online or in-store based on their age? Here we go. Here's my table. With these numbers, F11, F12, F21, F22, here's row 1, row 2, column 1, column 2, and my grand total. That's the way this table is set up. Do me a favor. Throw these into Excel. Let's build this table in Excel. These are referred to as the observed values. Again, this data is on our Word document, so you pull it off and copy it into Excel. Here it is. For a moment, let's ignore the observed values and only look at the totals, the outside edge, the bottom and the right. Just those 5 numbers for the moment. I want to test if these are independent or if they depend on each other. Assuming that there is no relationship between age and location preference for shopping, what would I expect? Well, my expectations are based off of the column totals and the row totals. So here, those are the same numbers we had above, right? I've just gotten rid of the middle. These ones up here, they're the observed. These are going to be my expected. Helps if I can spell. I had 50 people under 30. Right? That's what this number says right here. I had 40 people prefer shopping online. That's what this number says right here. How many people should be in that box? If age and preference are independent of one another. Well, 50 out of 100 is half, and I had 40 people there. Wouldn't I expect half of 40 to be in that box? The easiest way to do this is to take the row number times the column number and divide by the grand total. So I'm going to fill in this box with this number times this number divided by this number. And I should get 20 people. Let's fill in the other three boxes the same way. How many people should I expect in this box? In the over 30 category. I should also expect 20. But again, rather than just write down 20, I'm going to do the calculation. Row number times column number divided by grand total. Keep going. What should be here and here? Row number times column number divided by grand total. Here's my expectation. If there was no relation between age of shopper and whether they preferred being in there face-to-face or being online, I would expect numbers that looked like this. Again, now I can ask, does my reality differ enough from my expectation that these are actually related? Again, this is a new idea there's a new distribution, there's a new test. I don't know who came up with this description, but the name of this test is a chi-squared test. Chi is a Greek letter, looks like an X, only kind of cursive-y. Again, there's a long calculation that gets done here. I take the difference between the top table and the bottom table. I divide the squares of those differences by the expected values. I add them all up, and then I check against the distribution table with the right degrees of, forget it. I want to do a test. Equals CHI, look at what comes up. A whole bunch of junk there, isn't there? There's the distributions. There's the inverse distributions, but there's the bottom one. The fifth one down there says chi-squared test. CHISQ dot TEST, parentheses. And all it asks me for is where's the actual data and where's the expected data. Here's the actual data, comma, here's the expected data. It's going to spit out a p-value. That's what this test does. It gives me the p-value the same way ANOVA gave me a p-value. If this p-value is small, I reject my null hypothesis. So now I need to ask, what was the null hypothesis again? I wrote it down before I started writing the table. We are going to test to see if the null hypothesis, everything's the same. These variables have no effect on each other. Our null hypothesis is that these are independent. So if my p-value is small, I reject that. And I say what? Say again? No, that's my null hypothesis. So if my p-value is small, I reject the null and I say that they are dependent, not independent. Okay. So go back to the Excel piece and I say do the test. That's the p-value. Are these two dependent or independent? Are they related somehow or not? They are related. Remember that E. That E means I've got to move the decimal place over. In this case, 5 spots. So that's 0.00004. That's way smaller than 0.05. So these are dependent. What does that mean? It means that the age of the shopper affects whether or not they want to shop in store or online. I can't say which way it goes, but then I look at this bar chart, this column chart, and I say, well, I'm pretty sure that there's a clear preference for people who are over 30. They want to shop in store far more than people who are under 30. So younger shoppers prefer to shop online. Older shoppers prefer to shop in store. Where younger and older, in this case, the dividing line is 30. If I wanted to break this down better, if I did a larger sample, say instead of 100 people, I did 1,000, I could break those age ranges down more. 18 to 25, 25 to 35, 35 to 50, 51 and up. I could do all sorts of breakdowns like that. I probably will see a larger number of people shopping online, say from ages 65 to 85. But I don't know. If I were going to do the square manually, I would do that. I'm not going to do that part. But there's my expectation right there. This is the next one down on our formula sheet, on the document on our Canvas page. I have 2 training programs for an exam. Does one of them have a better pass-fail rate than the other? If you do program A, are you more or less likely, or does it make no difference to your passing versus program B? Now, I got a hunch based on that picture, but I don't have a proof. I don't have a test. I don't know whether my evidence supports it or not. So you tell me. In order to do a chi-square test, I need the expected frequencies to go with my observed frequencies. So, I need you to build me a new table. What do we get?
$7.5 and 12.5.
For here, you went this way for the 12.5, right?
Yeah.
Row times column divided by grand total. And now I can do my chi-square test right here. Expected values, sorry, observed values, then expected values. What does that mean? Felix? I reject my null hypothesis. My null hypothesis was that these were independent. So this means they do depend on one another. I rejected the independent part. And that means that which training program you use does affect your pass rate. This now justifies my picture from the bar chart where I say, oh, look, program A has a much higher passing percentage than program B does. Or say it the other way, program B failure percentage, that orange bar, is much higher than that of program A. So if you want to make sure you pass, use program A, not program B. If I'm a vendor for program A, this is going to be right at the top of my sales material. I was looking for 0.05. I got 0.0005. Yeah, there's a strong relationship here. The smaller the p-value, the more likely there is a connection. I took out more decimal places with the chi-square in this version. Please notice I am not restricted to just 2 in either rows or columns, and as many as I want. Do this one. The response here, yes or no, is some campaign issue. Which way would you vote, yes or no? This time I'm going to have 6 expected frequencies as opposed to the observed. Does where you live, which region you live in, make a difference as to which way you're going to vote? If I accept my null hypothesis, the answer is no. If I reject it, the answer is yes. Felix. It doesn't matter. Why?
Less than my p-value is equal to 0.05.
It is? Did I do something wrong? It's possible. Let's take a look. 50 times 75 divided by 150 is 25. Those are uniform, aren't they? All the way across. If nothing made a difference, I should see a 50-50 split in each region. What p-value did you get, Felix?
0.13.
Equals. Did you get the same expected values I did? Okay. Chi-squared dot test, parentheses, actual range, comma, expected range. Oh, so yes, I did something wrong. What did I do wrong back here? Oh, I see what I did wrong here. Wait a minute. Let's take a look. Do you see what I did wrong? Yeah, that's important. I f***ed up. I forgot one of the regions, didn't I? I only have 4 data values highlighted instead of 6. I'm wrong. Thank you. Hey, it's important. If I'm going to, no. But you see how easy it was. So, the region I live in does not dictate which way I'm going to vote on this issue. But if I go back and I look at that picture, wouldn't you say that there's a difference based on region? I wonder why the overall statement was it really doesn't matter, when it sure looks like it should matter. Felix, ideas?
Auch, dass the yes votes higher and Ralph has the no votes higher.
They kind of balance each other out, right? If I went back and did 3 different two-way tests, if I only compared north and south, which by the way was what I had done, then my answer would be yes. North versus south makes a difference. But north versus east and south versus east, those wouldn't. So the overall lends itself to there's more no, they don't matter than yes, they do matter. This is one of the important issues to be careful of when looking at more than 2 things here. It may look substantially like there should be a difference, but that p-value tells me no, really there isn't. Questions? We keep saying a picture's worth 1,000 words. Making those column charts helps me visualize what's going on, but it doesn't nail it down as specifically as a test result does. It would be nice if, let's say I did another survey and these values changed, if I didn't have to rerun the test every time, if my chart would update itself. That's the sort of thing we will eventually be able to make. We'll make live interactive dashboards that work with our data as the data updates. So if you were doing this process over the course of several days, you could update that every time new information came in. This is the sort of thing we see in actual real-time results behavior, election results, right? Oh, we see this at 9 o'clock in the morning. Now it's 11 o'clock. Now it's 3 o'clock. Let's start looking at what's going on. Dr. Burns created for us a general version. Oop, that's my examples, wrong one. No, that was the button. I just had this up in front. Go away. There it is. This does it all for us. It's on our Canvas page as chi-squared table. If you want to download that and hang on to it, that's useful, because then all you have to do is fill in the observed behaviors. So based off of that last example where we had 3 columns, I can just fill in as long as I fill them in correctly. Notice it generated the expected frequencies automatically. Further down, it gives me all of these behaviors, and it gives me that p-value all the way at the bottom. And it tells me, hey, what does that mean? There's no significant connection between these two variables. You should save this. Questions? When I go out and I communicate with people who are not as math-oriented as I am, I have to remember that I need to make sure I take what are complicated techniques and complicated results and phrase them as nicely as I can. That's part of the reasons I'm using all these images. But it's important to remember that I need to interpret my result carefully, because bad interpretations lead to bad decisions. If I had made the north versus south the centerpiece of my presentation there and said, hey, look, north versus south is going to make quite a difference here. I should do more advertising for my side of the issue, whether that's the yes or the no side, in those regions, but overall it wasn't going to matter, then I'm wasting money. The other piece of that is called a confidence interval. I need to be able to explain to people, I believe my average or my proportion or my P is this number. So let's say I go out and I compute a statistic. I gathered my information. Average consumer satisfaction rating is 8.5. The proportion of people who like my product is 72%. I have these numbers, but I did a sample to get those numbers. How sure am I? This number that I have, this is a point estimate. It may be that my actual, if I asked everybody customer satisfaction, wouldn't be 8.5, it'd be 8.3. If I checked with everybody, maybe the actual proportion of people who like my product isn't 72%, it's 70%. Those are not a big difference, but they are a difference, right? So I need to be able to express how confident I am that the number I got is right, that it reflects everybody, not just my sample. So I'm going to give myself a little margin of error. And I'm going to base the margin of error on how sure I want to be. So I go out and I do my estimate. My statistic says 8.5 is customer satisfaction. If you want to be 90% sure that the right value for everybody is in the range you're going to give me, then you could give me two numbers, one on either side of 8.5, and say, well, it really could be between 8.2 and 8.8. If you wanted to be 95% certain that the right answer was in there, you might need to go out a little further. You might have picked a bunch of people that really like your product, and the average is as low as 8 or as high as 9. If you wanted to be 99% sure, you might have to go out further still, right? Those are my levels of confidence. My level of confidence tells me how far out I should go from my point. So I have this point estimate here. And I'm going to say, well, I should go up or down a certain amount. That's my margin of error on either side. What I have now created is an interval estimate. I am X% sure that the parameter average is in this interval around my statistic. The bigger your X value, the bigger your confidence, the wider that interval gets. The question is, how do I get that? Well, that comes from our t-distribution. Most of the time. We can also do it with the normal distribution, but that means we have to make some assumptions about our population. Got 3 minutes. I'm going to put doing this calculation off until Tuesday. So we will pick this up then. The rest of Tuesday, after I walk through confidence intervals, is going to be spent looking at the project. 2 notes. The project for module 3 is actually a cumulative project, not a single module project. So we're going to move everything from module 1s, 2, and 3 together. I would recommend that you create a small group to work in. Each of you still have to submit your own project result. Read this carefully before Tuesday. Email me groups of say 4 or so that I know who's working with who. Everybody should be working together. When you do this work together, you should create a Google document that you should share with each other and with me so that I can see your conversation. So I know what you were thinking about as you did this rather than just sitting here and talking, right? Write down your discussions so I know how to look at how your group worked together. We'll see you all Tuesday. Have a wonderful week.